They're literally everywhere. In the fuel for our cars, the disinfectant in our medicine cabinets, even in our favorite drinks. But what exactly are alcohols, chemically speaking? Today, we are diving deep into the chemistry of one of the most vital groups of molecules in our world. So think about it for a second. You've got the ethanol in a martini, the isopropanol in rubbing alcohol, and ethylene glycol in antifreeze. I mean, these things do wildly different jobs. So what's the deal? What's the one chemical thread that actually ties them all together? Well, it all comes down to this little powerhouse, the hydroxyl group. It's just one oxygen atom bonded to one hydrogen, tacked onto a carbon structure. This simple little OH group, that's the signature. It's what makes an alcohol, and it is the key to basically everything that follows. Okay, so if they all share this one key feature, how do chemists even begin to tell them apart? Well, they've come up with a system, kind of like a chemical family tree, for classifying every single alcohol into these neat, predictable categories. Let's break it down. So, the first branch on our family tree is actually the easiest one. We start by just doing a simple count. How many of those hydroxyl, or OH groups, can we find on the molecule? If a molecule has just one OH group, like the propanol you're looking at here, we call it a monohydric alcohol. Mono just means one. See? Pretty straightforward. Now, what do you think happens if we add a second OH group? Well, it becomes a dihydric alcohol, but a lot of chemists just call it a diol. Di means two, so you can probably guess where this is heading. And yup, with 3 OH groups, we get a trihydric alcohol. A perfect and really famous example is 1,2,3-propantriol, which you've probably heard of by its common name, glycerol. So, that's our first level of sorting. Mono, di, and tri. Simple enough. But just counting the groups, that's only scratching the surface. For the most common type, those monohydric alcohols, the story gets way more interesting. It's not just that there's an OH group, it's where it's sitting on that carbon backbone. And that location, believe me, changes everything. This next layer of classification gives us 3 more absolutely essential categories: primary, secondary, and tertiary. And you'll often see them abbreviated with those little degree symbols. This is all about the chemical neighborhood that the OH group lives in. So what's the big deal here? It all comes down to the carbon atom that's directly holding on to that OH group. Is that carbon attached to just one other carbon, like in a primary alcohol? Or is it really crowded, connected to 3 other carbons, like you see in a tertiary alcohol? It might seem like a tiny difference, but it has a massive impact on how the alcohol reacts. It completely changes its chemical personality. All right, so we can sort them into all these different categories, but how do we talk about a specific one? For that, we need a naming system, and chemistry has a very, very precise language for this. You'll often see alcohols with 2 different names. First, there's the common name, like N-propyl alcohol, which is kind of like a nickname. Then you've got the official systematic name from IUPAC. The IUPAC name, like propan-1-ol, is like a complete blueprint. Propan tells you there are 3 carbons. Ol tells you it's an alcohol, and that little 1 tells you exactly which carbon the OH group is on. It's a universal language for chemists everywhere. Okay, so we can sort them and we can name them. But where do they come from? How are they actually made? This isn't just about mixing stuff together and hoping for the best. No, this is molecular architecture, and some of these recipes are so brilliant, they've actually won Nobel Prizes. To build these molecules with such incredible precision, chemists have a whole toolbox of really powerful reactions. And one of the most famous and most versatile tools in that whole box is the Grignard reagent. Its discovery by Victor Grignard was such a huge leap forward for building molecules that he was awarded the Nobel Prize for it way back in 1912. It's that important. And, the recipe for this Nobel-winning tool is surprisingly simple. You take an organic halide, you add some magnesium metal, and you just watch as that magnesium atom cleverly squeezes itself into the molecule. And just like that, you've made a Grignard reagent, and it is ready to work some serious chemical magic. So here's where it gets really, really cool. You take that Grignard reagent you just made and react it with the simplest aldehyde there is, formaldehyde. And what do you get? Boom. You've just built a primary alcohol from scratch. But what if you don't want a primary alcohol? What if you need a secondary one? Easy. You just swap out one ingredient. React that exact same Grignard reagent with any other aldehyde, and now you get a secondary alcohol. And for the grand finale, take that Grignard reagent, react it with a ketone instead, and you've just built a tertiary alcohol. I mean, this is the power of synthetic chemistry right here. One single tool gives you precise, predictable control to build all three classes of alcohol. It's incredible. Okay, so we know how to classify them, name them, and even make them. But that leaves one huge fundamental question. Why do they behave the way they do? Why are some soluble in water? Why do they have such high boiling points? The secret lies in an invisible force. Just take a look at ethanol. For a pretty small molecule, it has a really high boiling point of 78 degrees Celsius. Now, compare that to a molecule of a similar size, like ethane, that doesn't have that negative OH group. It boils at negative 89 degrees. So what gives ethanol all this extra stickiness that holds it together as a liquid? The answer is hydrogen bonding. Because of that OH group, the oxygen end of the molecule is a little bit negative, and the hydrogen end is a little bit positive. This polarity creates this powerful magnetic-like attraction between neighboring alcohol molecules. And it takes a whole lot of extra energy, in the form of heat, to break all those bonds apart so the liquid can finally turn into a gas. And you can see this trend perfectly in the data. As the carbon chain gets longer and longer, from methanol to pentanol, the boiling point just keeps climbing higher and higher. That's because the bigger molecules have more surface area for those hydrogen bonds to grab onto. But now look at the solubility in water. It does the complete opposite. That long, oily carbon tail starts to overpower the single polar negative OH group, making the alcohol less and less willing to mix with water. It's this perfect balancing act between two competing forces. So, there you have it. From the way we sort them, to how we build them, to the invisible forces that make them tick. It's all about that OH group and where it lives. Understanding that helps us use them for everything from medicine to manufacturing. We know what makes them stick together, but that leaves one last really big question for next time. What happens when you try to break them apart?